All right, so welcome. Thank you for joining us today. Day one of a multi-day quantum bootcamp. My name is Ann Buckhouse. I'm the Training Education Manager at the Pawsey Supercomputing Research Center here in Perth, Western Australia. We have an exciting and full agenda to cover. Prior to getting started, we have a tradition, it's an Australian tradition, to begin by acknowledging that I'm recording this webinar, from the traditional lands of the Noongar Whadjuk people. I pay my respects to their elders past and present, and I would like to extend this acknowledgement to all traditional owners of the various lands on which each of you live and work today. And if you'd like, you can share those in the chat. The link to the detailed agenda was emailed to you yesterday. In summary, this week we'll be focused on three main goals: learning about various popular quantum algorithmic techniques, discussing the potential advantages of quantum computing and when these advantages might be realized, and identifying the types of problems these algorithmic techniques might be applied to. The discussions and tutorials will be led by quantum experts from AWS and SoftServe. They'll be introducing themselves shortly. You will have access to AWS quantum resources for your hands-on exercises. There will be opportunity for you to work with the group and solo. Please enter any questions you might have or any access issues when we get to accessing Braket into the chat. The session is being recorded, so we ask that you please mute your microphones. I'd like to now hand over to Dr. Pascal Elahi to give a brief introduction to Pawsey and quantum at Pawsey.
Thanks, Anne. Hello, good day, everybody, and welcome to your exciting quantum adventure with training provided by Pawsey and SoftServe and AWS. So Pawsey's quantum strategy is actually quite manifold. So we are looking at classical computing and integration of quantum computing into that classical framework, which involves the complexities of job scheduling, of offloading computation to the QPU, and to an extent also doing quantum algorithm research, because we want to make efficient use of quantum computers and figure out problems which they're tailored for, like they're optimized for, to complement essentially the computing you would do at HPC centers. Part of this is also then lowering the barrier of entry for everybody who's kind of not necessarily a quantum computing expert. And that's the reason why this bootcamp exists. We are trying to make sure that people feel comfortable possibly using new infrastructure that's coming up online and feel comfortable making use of these rather new technology. And the idea is we're going to provide this through access to quantum computing, so like high fidelity simulators and emulators and on-prem systems, as well as access to AWS Braket. Now, that isn't the entirety of things, but that's essentially the big focus: training and also providing the infrastructure. And we hope that everybody here can make use of the infrastructure we'll provide and hopefully make use of quantum computing. And on that note, I'm going to pass over to our quantum computing visitors and experts from SoftServe and AWS to take this bootcamp forward. They'll share the screen. We'll be here to provide support, and please feel free to ask questions in the chat. It's very important to have a conversation about complex topics, and I think it's really important. So feel free to always ask questions. We'll do our best to answer them. Thank you.
Thank you, Pascal. And we will now turn over to our colleagues at SoftServe.
Hello, everybody. Please give me a second while I share my screen. Okay. And everyone see my screen?
Yep.
Okay. Hello, everybody. So SoftServe, SoftServe is a tech consultancy company. We are actually a pretty big company. We have about 13,000 people worldwide. We do many things. These are quite a number of things that we do, and we have many offices all over the world. So currently, the APAC office is based in Singapore, and the APAC office is where we're running the bootcamp from. Specifically within the R&D portion, we have a quantum team that is about 15 people strong. We have about 10 full-timers and 5 part-timers. And we collaborate with many universities, consultants with many universities, and we pursue many directions, and we pursue a lot of partnerships and academic connections in order to build up the quantum R&D team. Our main services that we offer at the quantum R&D team are these main 4 services over here. But the idea behind it is that no matter where you are in the quantum journey, we try to be there and help you, be it at the start when you need to do some consulting and workshops, in the middle where you want to look deeper into algorithms for your use case, or whether you want to evaluate your hardware. The conversations that we've had throughout our many partnerships has led to many interesting events. One of the most interesting events that we've held before is the Quantum Bootcamp Singapore, which we held in from May to July last year. And after talking to Pawsey, after talking to AWS, after talking to Pawsey for some time, we decided that we wanted to recreate a similar experience here. So these are just some of the research directions that we've taken. So today, we have myself. I'm Jonas. I'm the quantum team lead at SoftServe, as well as the APAC R&D lead. I lead the quantum initiatives worldwide, and I lead a lot of the R&D initiatives within the APAC region, including this bootcamp. And today, with us today, we also have Dikshan. So self.
Lovely. Can you guys hear me?
Okay.
Okay. So, yeah, we're in the same room, so very convenient. So my name is Dikshan, as Jonas mentioned. I'm a research engineer in SoftServe, and I specialize in quantum computing. I work with a startup that does software development. I am our error mitigation expert, but I've worked with algorithms specifically in variational algorithms before. Yeah, and I will be working alongside you guys, lecturing, providing code, and working through them together throughout this bootcamp. So looking forward.
Yeah. We look forward to a fruitful session with a fruitful week with all of you. Fruitful 2 weeks for some of you, actually. And now we hand over to Carl Watt, Director of Solution Architecture at APJ at AWS Public Sector. Thank you.
Thanks, Jonas. Appreciate the introduction, and wanted to thank Pawsey and SoftServe for participating with us and in providing this session. I think it's a great idea to share this information and provide this introduction to a great new technology. Just wanted to give a couple of points on Amazon's approach to sharing technology. So firstly, we have a focus on democratization of technology. And this means that we make the technology available to anyone, anywhere. So within our cloud computing services, anyone's able to get access to that. And we've extended that now to quantum topics and offer multiple different quantum computers within the Braket service. So during this week, hopefully you'll get to understand a bit more about what those do. One of the reasons for this is that different quantum computers have different strengths. And we believe that some of those strengths will be differently applied in different algorithms. So I'll give you some insights into how some of these technologies may evolve over time. The second point I'd like to kind of talk about is that the reality is that quantum computing is going to be used as a hybrid with high performance computing. So traditional computing and quantum computing together. So in the medium term, we see the most likely applications as being combinations where an algorithm is partly done in the quantum way and partly done in the classical way. And so we see this as an augmentation of capability. And again, within cloud, it's very easy to combine those two components together and to run parts of your workload in quantum, parts of your workload in classical. And one of the benefits of doing this is that over time, as the quantum algorithms improve, as the quantum machines become bigger, you're able to move more of the optimization problems perhaps into the quantum space. The third thing I'd like to kind of emphasize is that, and this is really a great starting point here, is that we recommend starting with experimentation. So we understand quantum computers are not quite yet ready for production applications in many areas, but there are some production applications we can do today. However, quantum computing is radically different to any other style of computing, and it takes a while to get your head around exactly what that means. So we recommend playing with it, understanding it, experimenting with it, to really just get used to the way in which these algorithms can work, how the algorithms may then be incorporated into some of your more business algorithms that could be used for other workloads. So we do see these algorithms being applied. And one of the things I would say is that we're right at the start of this journey with quantum computing. So both new algorithms are going to emerge over time, as well as new applications for those algorithms where we solve problems we probably haven't even thought we could solve in the past. So with that, I'll pass back to Pawsey, and hope you have a great week or two. Thank you.
Thank you very much, Carl, for that introduction. Now, let's not hesitate. Let's jump right into the good stuff. Right, I will turn it over to our colleagues at AWS to kick us off.
Hi, Brajesh. Hi, everyone. This is Albert. I'm working with Pawsey to prepare this session. I'm very excited to see finally we coming to this stage. We have everyone here. I hope everyone have a pleasant and fruitful 2 weeks. So Brajesh, can you come to the stage?
Yes, I'm here. Can you hear me?
Great. Yes, loud and clear. Please go ahead. Thank you.
Okay, thank you very much for giving me this opportunity to talk about quantum computing and quantum computing at Amazon Braket and at AWS. My name is Brajesh, and I'm a quantum applied scientist, and I'm really excited to be here. I've done one session with Pawsey last year, and I really thoroughly enjoyed it, and I'm looking forward to a great session with you all. So before I go ahead, a couple of logistics. I mean, while giving the presentation, I may not be able to look at chats. So if you have any questions, you can write in the chat. And Albert, would you be so kind to, stop me in the middle if there are any questions?
Sure, absolutely.
Okay. And also, feel free to unmute yourself and ask any questions, stop me in the middle. And I would like this to be more conversational than, just one way of, me talking all the time. So, and as the organizers already told you, we will be providing you with access to AWS, which will be active for next 72 hours. So you'll be free to, use that to experiment with, the service Amazon Braket and some of the examples that we will be going through today. And I believe in 2 days, tomorrow, you will have a talk from my colleague Sebastian Stern about the advanced topics, right? Okay, so now I will share my screen and let's see if you can see my screen. Are you able to see my screen?
Yes, we can see your screen.
Okay, perfect. And I will, now I'm doing a full screen. I hope you can see my full screen. Okay.
Looks great.
Okay, thank you. All right, so let's jump right in. Quantum computing at AWS. So in today's talk, in 2 hours or so, what I planned for you is to talk about very basic stuff, right? What we are doing in terms of quantum computing at AWS, what is Amazon Braket, and then I will show you how you can access to Amazon, get access to Amazon Braket, experiment with it, and I will demo you the Amazon Braket console. Then I'm going to assume, practically no knowledge of you. For any quantum computing background from the audience. So some of the advanced audience might find a little bit, repetitive, but at the end, I hope you'll get something out of it when I show you how to run tasks on simulators and QPUs. Okay, so in the middle, of course, if you have any questions, feel free to ask. Okay, so getting started with quantum computing. Quantum computing, as you already know or might have heard about, that it is based on very intricate physical laws that govern our microscopic atomic world, right? And quantum computing is based on 2 basic principles, superposition and entanglement. And the exciting part of quantum computing is that it's a new paradigm of computing. That is to say, the very fundamental way information is processed is different from the traditional computing. And this comes with some advantages. And the advantage is that there is a promise that there are certain class of problems, not all problems, there are certain class of problems which are hard to solve on traditional computers or even supercomputers. They can be solved with quantum computer in exponentially faster as compared to the traditional paradigm. And that is quite exciting. But please note that quantum computing is not going to solve all the problems, but there are certain class of problems that will be, more efficient to solve on quantum computers. Another caveat, or rather more understanding of quantum computing is that quantum computers are not meant to replace traditional computers. There are some tasks, like traditional computers are definitely going to be better than quantum computers, right? I mean, addition or multiplication probably will be always we will do with traditional computing, because the way quantum computing handles algorithms is fundamentally different than the classical computers, and there are certain problems where classical computers are much better than there are certain scenarios where classical computers will be more useful than just quantum computers. And at the end, in some sense, like the paradigm of quantum computing is going to be hybrid all the time, right? Because we might need classical computers to for pre-processing, post-processing, or handle the various tasks before using a quantum computer to run a quantum circuit and so on. So that's that. While quantum computing promises big advantages, it also comes with hard scientific and engineering challenges, right? These challenges involve not only building completely new hardware, but also rethinking algorithms in a fundamentally different way. For instance, if you look at factoring algorithm, the classical algorithm for factoring is nowhere close to what Shor's algorithm for factoring is, right? And this happens precisely because the way information is processed in quantum computers is fundamentally different from that in traditional computers. Now, we have just entered what is called noisy intermediate scale quantum era. That means basically is that we have quantum devices which are working. However, there are certain limitations there are many limitations to these quantum devices. First of all, being that they are very noisy, right? I mean, we haven't still mastered how to completely cut off noise or control noise in these devices. Second, they are intermediate scale, meaning that the number of qubits that these devices possess is of the order of a few hundreds at max, right? But to run full-fledged quantum algorithms, for example, Shor's algorithm, we will need thousands or even tens of thousands of very high-quality qubits, logical qubits, which may mean that you would need hundreds and thousands of physical qubits to run your algorithm. Nonetheless, NISQ-era devices are great to run POCs, proof of concept projects, and get ready for the next phase of quantum computing. At the same time, in today's research, where people are also spending time thinking about in what ways we can use these intermediate devices to maybe gain some kind of advantages from quantum computers. And that would be the topic of the second part of this session that my colleague Sebastian Stern will be talking about is hybrid quantum classical computing, where he will be talking about QAOA or other hybrid algorithms using which NISQ devices can be useful to solve some of the problems probably in near future better than traditional classical computers. So why is quantum computing so interesting? Because it has application in many areas. right? The original motivation behind quantum computing, when quantum computing was proposed by Richard Feynman in the 80s, was to simulate nature, right? Nature at its fundamental level is quantum mechanical. And Feynman's point was that if you want to simulate quantum mechanics, you better have a device which obeys or follows the laws of quantum mechanics. Because to process and store quantum information on classical computer, it becomes exponentially hard when the size of the system increases, right? So with that, I mean, if you have a quantum computer, the first applications people thought about was to simulate molecules and find out the ground state of electronic Hamiltonian and so on. And that was like computational chemistry. Then that led to a natural extension to material science, right? Finding new kind of materials and so on and so forth. So, I mean, apart from like the physics and scientific applications, there are like mathematical problems which also can be very beneficial, can be benefited from quantum computing. And that is like one of the avenues is optimization. And optimization, like one of the very popular algorithms with NISQ devices is called quantum approximate optimization algorithm, which my colleague again Sebastian will be talking about in the second part of AWS talk, maybe tomorrow. So like optimization is, we know that it's everywhere, and maybe using NISQ devices in near future, we will be able to beat traditional computers on certain optimization tasks. So, however, like to run, as I talked about, to run full-fledged optimization algorithm, one would need fault-tolerant quantum computers, which will require hundreds and thousands of high-quality qubits, which we don't have yet, right? And if we look at the progress of quantum computing in terms of the hardware, this diagram kind of shows where we are and where we want to be. So in this diagram, I mean, on x-axis, I'm showing number of qubits, that is the quantity, and on y-axis is the quality. So quality is in terms of error rate, right? So lower the error rate, higher the quality of the qubit would be, and higher the number of qubit, better it would be, right? So where we want to be is like we want to have very high number of qubits, but very low error rates. So that is the end goal, region number 3. That's where we want to be. That's where all the fun part is. Like we have where we have high quality qubits, where we can do fault tolerant quantum computing and so on and so forth. We have just passed the region 1, right? The phase 1, where we either had very few qubits of very high quality or large number of qubits of very low quality. So that was the region number 1. And currently, what we are is in the near-term applications. So region 1 is very easily classically simulatable. One can simulate those like a few qubits, like 10 or 15 qubit circuit very easily. 3 would be the quantum computing with error correction. And region 2 is where we are right now, near-term applications. And with the error mitigation and like better and better quality of qubits coming in, it is expected or hoped that in the near future, we may be able to get some kind of a quantum advantage with near-term devices on certain tasks. But before I go ahead, I would like to pause for a minute here and ask if are there any questions?
Hi, Brajesh, there's a comment in the chat. The error rate you mentioned it still looks very high compared with conventional computer.
Okay, again, let me just look at the chat. Error rate is still very high compared to conventional computers. That is right. I mean, error rate is still very high, but this like 10 to minus 4 is like being 99.9999% of error, which would be like good enough to do a fault-tolerant quantum computing. at least to begin with. And this is the error rate we are talking about in the physical qubits. So with many physical qubits, one may be able to have like fault tolerant logical qubit. Did I answer the question? I suppose yes. Okay. All right. So going back to the presentation. So what we are doing in terms of quantum computing at AWS, right? So quantum efforts at AWS have been existing for like over like 4 or 5 years now, and we have like 4 different pillars, as you will, if you will. First is AWS Center for Quantum Computing, where all the research and development happens for computing technologies. People are working on fault-tolerant quantum computing, and we are also trying to build a quantum device. Then we have AWS Partner Network, which is basically a community of partners who are interested in quantum computing, and so the partner network works with those partners and help them and find solutions and so on. Then we have Quantum Solutions Lab, which is the state-of-the-art part of Amazon Braket or AWS that focuses on finding out interesting quantum and classical solutions to problems of our customers. Then at the end, Amazon Braket, which is what I'm going to talk about in the rest of the slides today. So Amazon Braket is a fully managed service by AWS, where we provide access to simulators and quantum hardware for you to experiment with quantum computing and build solutions. So without further ado, let's talk about Amazon Braket. So Amazon Braket is a fully managed service. By fully managed service, I mean that all the networking, provisions of computing resources, safety and security of the network, of the cloud, and everything is totally managed by AWS. All you are in charge of, or need to worry about, is just accessing Amazon Braket, bringing your own data, and write your own code. Rest of all the low-level stuff is all managed by AWS. So this fully managed service is brought to you by to make it easy for users and scientists to explore quantum computing. So there are like 4 stages you can do. First is you build, you can build your programs using Amazon Braket SDK, Jupyter Notebooks, or command line interface, and I'll be showing you how we can do that using Jupyter Notebooks. Then you can test your algorithms and your program using local simulator or high-performance simulators that we have available. Then you can run those programs on QPUs, quantum hardware, and at the end use various services and features of AWS to analyze your program, like monitor your algorithms and analyze your results and so on and so forth. Yeah. Okay, so before I talk about Braket architecture, are there any questions so far?
There's a question in the chat. Number one, does AWS have a simulator or actual quantum computer? I think we have both. And the next one is how scalable is the fact that having so many qubits just to lower the error rate to 1 minus 4. Okay, so the first question, does AWS have a simulator and a quantum hardware? So Amazon Braket provides access to simulators like as I will be talking about, state vector, tensor network, and density matrix simulators, which are built in-house. You are also allowed to bring use embedded simulators. For example, there are simulators from Penny Lane that you can utilize. So that's that. In terms of hardware, Amazon Braket provides access to various kinds of hardware from third-party vendors. We'll be talking about that as well in a minute. At the moment, Amazon doesn't have its own quantum hardware that is available through Amazon Braket, but that might change in future, so stay tuned for that.
For the second question, how many, if I understood the question correctly, the question was how many physical qubits are required to control error with the error rate 10 to minus 4. Okay, so the answer to that question is unclear because that depends on the fault tolerant algorithm as well. I mean, what I showed you was like more of a representative information that was not like a very quantitatively sound graph. That was more like to show that we need lower error rate and higher number of quantity of qubits in order to build fault tolerant quantum computing. Did I understand the second question correctly? If not, I can, try again.
So Richmond, maybe you can just unmute yourself and see if this addresses your query.
Hello, hi. Yeah, just wondering, because you showed that you use quite a lot of qubits just to lower the error rate. So I'm just wondering, like, I mean, looking at the number of qubits, like 1 million qubits, is it like something physical? Like, can you achieve that just to lower the error rate, just to like 0.001, something like that?
Okay, so yeah, I understand the question. So it's not like we need 10 to the 6 qubit to lower the error rate to be 10 to minus 4. We need 1 million of qubits with error rate 10 to minus 4 to achieve fault tolerant quantum computing. So we need many qubits, millions of qubits, and we need all the qubits to have very low error rate of the order of 10 to minus 4 to do any useful quantum computing. That's the statement we are doing here. Okay?
Right, thank you.
Okay. I mean, just increasing the number of qubits is not going to help you, build a lower rate, right? We need both high number of qubits and high quality of qubits.
Excuse me, can I ask a question?
Sure.
I'm not sure about the answer to my question. I asked how the platform we're using, which is AWS, does it have a simulator, or we'll be working with the actual computer? So I heard two answers. The first one was it has both, and the second one you said that it doesn't have the quantum hardware. The actual quantum hardware is more of like simulating the rules. I'm confused. Which one is the correct answer? And are we working, my specific question is, are we working with the quantum hardware or no? It's just a quantum simulator.
Okay. Thank you for the question. Okay. So to answer your question will be answered like in next 10 minutes when I talk about in more detail about the service, but let me answer you very quickly. Yeah, the answer to your question is Amazon Braket has access to both simulators and quantum hardware. Quantum hardware that we have are from different vendors, like different third-party providers. For example, from IonQ, from Oxford Quantum Circuit, from Quera. So these different companies, they are building quantum hardware. They have built quantum hardware, and you can access those quantum hardware through Amazon Braket.
Thank you.
Amazon, so far, we don't have Amazon's own quantum computer being offered through Amazon Braket, but that might change in future. That's the statement at the moment. Is that clear? Okay, I hope that is. So in the interest of time, let's move on. So let's talk about Amazon Braket architecture for a bit. Yeah. So you as a user, I mean, you will access to Amazon AWS Cloud first. So AWS Cloud has, inside AWS Cloud, there is Amazon Braket, which is a service that interacts with many other services. Like if you're available, if you're aware of AWS services, Amazon CloudWatch, EventBridge, S3 for storage, IAM for like access management and permissions, and the key management service, and so on and so forth. Amazon Braket itself, within the cloud, has simulators. So these simulators are classical simulators that use Amazon EC2 instances to simulate a quantum hardware. And then we have hybrid algorithms, hybrid jobs, basically a feature that you will learn more about in the second part of the talk tomorrow. So Amazon Braket as a service within the cloud has access to simulators and have hybrid algorithms. Quantum hardware is not part of AWS cloud because quantum hardware is current quantum hardware is provided by third-party providers, which have labs located at different geographic locations. But Amazon Braket has direct access to those quantum hardware through safe and secure network. So you as a user, you interact with Amazon Braket, right? Either using managed notebooks or your local IDE or Amazon Braket console. You interact with Amazon Braket, and then in the backend, like Amazon Braket, interacts with this quantum hardware, and you don't really need to worry about how this communication happens. Access to quantum hardware is like a part of Amazon Braket. Okay. Now, so available quantum hardware, we have like 4 different modalities of hardware available at the moment. First is IonQ, that's an ion trap QPU. There is one Harmony that is 11 qubit, Aria is 25 qubit, then Brajesh, which is currently down at the moment, it's a 79 qubit superconducting QPU. Then you have Oxford Quantum Circuit, that's an 8 qubit superconducting QPU. And at the end, we have a device, analog Hamiltonian simulation device from Quera, which is 256 qubit device. So the rationale here is that to be able to provide different modalities of quantum computing hardware, for you to be able to experiment and compare and contrast your algorithms across various platforms. Then, before running programs on quantum hardware, since quantum hardware is a scarce resource at this moment, you can run your algorithms on simulators. First is local simulator. So local simulator is part of Braket SDK. So when you install Braket SDK on your local laptop, you get this local simulator for free. You don't have to pay anything for that, right? So the local simulator it's a fast and convenient way of prototyping your algorithms because it uses your local infrastructure of your laptop and so on and so forth to simulate any quantum network. And for that, you don't need access to AWS cloud. However, since local simulator, it depends, the capacity is limited by your local laptop, you may be able to go up to 15 to 20 qubits in terms of simulation. But if you want to go higher for higher performance, you could use one of these state vector density matrix or tensor network simulator, which is part of Amazon Braket AWS cloud. So to access SV1, DM1, and TN1, you would need access to AWS cloud, and I'll show you the pricing information for that as well. Okay. Now, Amazon Braket SDK, basically it's an open source Python library that you can very easily install by pip install. It comes with 3 free local simulator, Braket_SV, that's a local version of state vector simulator. Then Braket_DM is a local version of your density matrix simulator, and Braket AHS is analog Hamiltonian simulator, right? So you can ask, like, what's the difference between state vector and density matrix? So the idea is that density matrix simulator has the capability of simulating noise. So you may be able to, you can simulate noise also using one of these density matrix simulator. And AHS is analog Hamiltonian simulator that simulates the neutral atom devices, which is based on completely different paradigm of quantum computing. Which is different from like the gate-based quantum circuit model. Then Amazon Braket also comes with enhanced functionalities such as integration with open source plugins such as PennyLane, which is the leading software package for quantum machine learning and training neural networks and so on and so forth. So PennyLane is part of Amazon Braket. So when you install Amazon Braket, you can, Penny Lane comes with it. So you can use Penny Lane in Amazon Braket as well. If you're fond of Qiskit or you have developed your code in Qiskit, there is also Qiskit Braket provider. So using Qiskit Braket provider, you can import your Qiskit code directly to Amazon Braket and take advantage of various simulators and all different available quantum hardware to run your program. Okay, now let's get to the interesting part, access to the workshop environment. But before I do that, let me ask if there are any questions.
Josh, there is a question from the chat to have a better understanding of quantum hardware computational power. How each qubit is comparable to conventional computational power measured in flops. Is there a sensible comparison at all?
That is an interesting question, and as I mentioned, it's not the same paradigm of computing. So comparing flops versus how qubits work is not the right comparison. I joined.
There's another question. Is there any source to get slides and teaching materials?
I'll be showing you the workshop environment in a bit. You could look at the teaching materials and download these notebooks before the next in the next 72 hours. So, and if you want, I can also share the slides. I can send the slides to Albert, and Albert can distribute them.
Thank you.